Dear professors and guests, nice to meet you. I'm Chao Yip, and this is my teammate Zhu Hinto. We are from S.K.H. Lemwu Memorial Secondary School. Our paper is From Happy Function to Linear Happy Functions. The happy function small hx is a function that maps positive integers to the sum of the squares of its digits in base B representation. If an input x returns 1 after some iterations, it is called a happy number. This problem has already been solved by mathematicians. Therefore, our team would like to investigate some generalizations. We generalize the happy function to be the linear happy functions big hx, which was studied in our paper. The linear happy functions multiply a constant p and then minus another constant q to the original happy function. We aim to find the conditions of p, q, and x such that after m iterations, big hx will map to 1. And for a more stable behavior of big hx, we first fix p to be a positive integer. To find the existence of happy numbers with different values of q, we proved in the following cases there is no happy number. When q is negative, when q is less than p minus 2, and when q equals p is greater than or equal to 2. However, there are happy numbers when p and q are both equal to 1. In proving its existence, we found that for any positive integer s, we can always find a positive integer x such that small hx is equal to s, and there are infinitely many of such x. So now, we have two more cases to tackle, when q equals p minus 1 and when q is greater than p. We first consider the case when q equals p minus 1. We find that x is happy if small hx is equal to 1, and this happens only if x is in the form of b to the power m. That means the representation of x in base b must be a 1 followed by m zeros. We call such x trivial happy numbers. Then we look for some more interesting non-trivial happy numbers by iterating big hx twice. If the equation h2x equals 1 has solutions, we found that p must be a factor of b to the power t minus 1. By considering its factorization, we examine whether b to the power t minus 1 is divisible by p. We claim that it is divisible by p if and only if b and p are coprime. And in order to prove this, we first prove the following two lemmas. In lemma 4.4, we prove that among the p terms shown here, at least one of them will be divisible by p. We prove by contradiction. If none of them is divisible by p, then by taking mod p, their values can only be 1, 2, 3 up to p minus 1. As there are p terms, by pigeonhole principle, there must be at least one pair of the terms congruent in mod p. So consider the difference between those two terms. On one hand, the difference must be 0 under mod p, or say divisible by p. But on the other hand, after the 1 and some of the b terms cancelled out, we can take out the common factor b and factorize. The term here is not divisible by p, as b and p are coprime. And the netted term is also not divisible by p, as this is one of the terms in the previous sequence. Therefore, their products should not be divisible by p, and this results in a contradiction. So, there must exist t such that the sum of 1 plus b squared all the way up to plus b to the power t is divisible by p. Then we proved in lemma 4.5 that if b and p are not coprime, then this summation here is not divisible by p for any t greater than or equal to 2. Also, we proved that b minus 1 is not divisible by p. We can conclude that b to the power t minus 1 is not divisible by p. Together with theorem 4.3, lemma 4.4, and lemma 4.5, we can conclude that for q equals to p minus 1, the equation big h2x equals 1 has solutions if and only if b and p are coprime. Hence, we can find all the happy numbers within 2 iterations of big hx, and here are some numerical examples in the Denry system. Non-trivial happy numbers exist for all p if p and 10 are coprime. After tackling the case of q equals to p minus 1, we will consider the situation when q is greater than p. We have proved in theorem 5.1 that big hx equals 0 has solution if and only if q is congruent to -1 mod p. Then we look for the condition so that big H2x equals 1 must not have solutions. While we are trying to find different values of P, Q, and B, we have found that for these particular values, the happy numbers are only those shown on the screen with a special pattern. Obviously, the small hx is 2, so this will make them happy numbers by one iteration. But why is there no happy numbers by 2 or more iterations? We want to find out the reason and in what condition there is no happy number by 2 or more iterations. Finally, we have proved that for q equals to 2p minus 1, if there exists integer u such that u is greater than 3, a factor of p, and b congruent 1 mod u, then hmx equals 1 has solution only when m is equal to 1. That means all those happy numbers are only by one iteration. First, we have proved that the happy numbers exist in one iteration, and we found that as small hx equals 2, these numbers must have a leading digit 1, exactly one of the rest of the digits is 1, and other digits are 0. Then we can see that x asterisk congruent to 2 mod u. However, the output of big hx must be 1 mod u. Therefore, it is impossible to have big h2x equals 1, and hence there is no happy number with 2 or more iterations. Then we further proved a more generalized result. We used lambda to raise 2 in the previous theorem, and the statement is also true for all lambda greater than or equal to 2. The main idea of the proof is, on one hand, we consider x asterisk mod u by considering the sum of all digits of x asterisk, and show that it cannot be congruent to 1 mod u. On the other hand, by rearranging big hx, we prove that the output of big hx must be congruent to 1 mod u. Hence, it leads to a contradiction. We cannot find such x asterisk as a happy number by 2 iterations. So we can find all the happy numbers by solely considering the combinations of digits that satisfy small hx equals to lambda. Now we have understood the existence of happy numbers in all forms of P and Q. The results can be summarized in this flowchart. During our investigation, we found that sometimes big hx will return to an output greater than x. However, it should not occur when x is very large. Therefore, we investigate whether we can find a lower bound L such that big hx must be smaller than x for all x greater than L. Firstly, when one more digit is added to a number, at least a b to the power n minus 1 will be added to x, but at most a b minus 1 square will be added to small hx. Therefore, it is clear that x will be greater than big hx when x is large enough, and a more formal proof is given here. By proving this inequality here, we can show that big hx is smaller than x when x is greater than a given n-digit number L. Then we want to find the value of L. To find L, we need to solve this inequality here for n naught. And after rearranging, it will be useful if we can consider the Lambert W function. The Lambert W function is an inverse function of the function Vx equals to x times e to the power x. It has two branches when x is between -1 over e and 0. To use the Lambert W function, first we show that this expression here falls within the range -1 over e and 0. So we prove this by differentiation, showing that g prime b is greater than 0 for all b greater than or equal to 2. So we can attain the minimum by putting b equals to 2, and we prove the range of the right-hand side of the inequality we want to solve. Then we prove that the w-1 function is decreasing on its domain. Then we can apply it to the inequality concerned. And after some simplification, we find an expression of the lower bound L in terms of P and B. Here is an example to demonstrate how to find L, and we believe that this can help us to search all the patterns of all happy numbers with different linear happy functions and base. Thank you.